So today I'm going to be talking about what will it take to generate fairness-preserving explanations, and more broadly, how fairness and explanations might interact. So this is work I did while I was an undergrad at Brown, and this was a collaboration with Sohini and Hima from Harvard and my professor Stephen Bach from Brown. So to motivate this a little bit, the big picture questions we're asking in this work is, what is a good explanation in fairness relevant applications, and how can a good explanation be found? And so we were really interested in this because a lot of recent work on the potential end users of explanations and potential purposes of explanations have talked about applications like debugging or improving the model, or ensuring regulatory compliance, informing downstream actions, or justifying actions based on algorithm output. And in a couple places, we've also seen explicitly saying using explanations to determine whether the algorithm is being discriminatory or not. And sort of the motivation behind this was it's actually not super well defined what it means for an explanation to accurately convey the fairness of the underlying black box. So this work is sort of meant as an initial probe in that direction. So in situations where we do care about fairness, or in an application we're aware there's a fairness problem, what does the data actually look like? And so usually this happens when there's a meaningful difference in how the features or labels are distributed across demographic groups, or their joint distributions are different across groups. And what this causes is some performance disparity across groups, or classification disparity, whatever measure of fairness you choose to use. And also, another note I wanted to make here is that demographic information may or may not be used by the model, whether you're using sort of a fairness intervention or a fairness algorithm, or you're choosing to leave it out of the dataset, which is often the default today. And so I sort of wanted to give a super simple example of how this situation and fairness might interact with how we generate explanations. So this obviously is not going to be a real black box in any situation. However, let me just explain to you what's going on here. So what's plotted here is both the data distribution and the decision boundaries of this black box. So we have three features: x0, which is the horizontal axis, x1, which is the vertical axis, and group membership, which is, you can see there's like two clusters. There's a left cluster and a right cluster, and the left cluster is around 27% of the total population, so it's like a minority compared to the whole population. And the black box algorithm, what it's doing is saying explicitly, if group equals left, then you are classified as 1 if your x1 feature is above 6, but if you're in the right cluster, then you're classified as 1 if your x1 value is above 5. And so specifically I wanted to call out here that maybe this is like an example of a fairness intervened black box, because even though the two clusters are centered on different x1 values, that this decision boundary actually results in the same percentage of both groups being classified as a 1. And so the question is, what does Lime do with this decision boundary? So here's off-the-shelf Lime. I just pip installed it and applied it to all the points you see on the left graph. So what I did was take every single point, generate an explanation for it with Lime, and then use the coefficients from the Lime explanation to generate a prediction for whether that specific point would be classified as a 0 or a 1. So it's immediately obvious that this Lime decision boundary, there's actually only a single boundary across all the data points, even though, you know, in the black box there are two distinct boundaries. And furthermore, this boundary is actually closer to x1 equals 5, which is the decision boundary for the majority group. So you know, here's a reminder of what the actual equation for the decision boundary of the black box was. And again, you know, this decision boundary is simply wrong for both groups, and it's misleading, but perhaps it's worse for the minority group than the majority group. And so I guess the next question then obviously is, how would we define and diagnose a situation like this? How would we know when an explanation is being misleading and what does it mean for an explanation to be misleading. So one of the first things we wanted to think about was, if the model is unfair, the explanation should give some indication that the model is unfair. If it is fair, then the model shouldn't erroneously suggest that it is unfair. So the first sort of way we might look at this is group fairness mismatch. So with the example I just gave, the explanation provides an approximation of the decision boundary, and if it does that, then the approximated boundary should also result in similar group fairness metric values as the black box being explained. And so the other version is counterfactual fairness mismatch. If an explanation is generated for a specific data point, so this is different from the decision boundary argument, if an explanation is generated for a specific data point, then changing the sensitive feature value of that data point should also change the explanation in the same way that the black box classification changes. So this, it's probably worth exploring more what exactly the similarity metric we want to define this as. But for example, if the classification changes when you switch the sensitive feature value, then we should see some change that's meaningful and obvious in the explanation. And so if we go back to the example really quickly, just to give it an idea of how we might use those metrics to diagnose when there is a fairness mismatch. So if we're looking at fairness mismatch from the group fairness perspective and the counterfactual fairness perspective, we'll actually be able to find some problems with this LIME explanation. So with group fairness, the original black box is predicting y equal 1 at equal rates, but the LIME boundaries do not, and that's because of the offset of the clusters along the x1 axis. And if we looked at counterfactual fairness mismatch, we can think about a point in the left cluster with an x1 value of 5.5. If you switch group membership to being in the right cluster, that should change the prediction in the black box, but the LIME explanation doesn't really show that. So I think this is really useful because, in this very simple toy example, you might say, well, the reason why LIME learns a single line is because it, by definition, learns a single linear boundary. But I think the point is that, we can, if we use a shallow decision tree, for example, we might be able to perfectly approximate the black box. But my point is that we wouldn't even know that we would have to switch from the out-of-the-box linear approximation to something slightly more complex like a shallow decision tree, unless we did some evaluation like this and found that there was mismatch in terms of the fairness performance. Also, really briefly, I wanted to touch on some additional considerations in this sort of area that are worth more research. The first one is if the sensitive attribute is a part of the model's feature set, then if we get a feature importance value for that, how should we interpret that? Because if the feature importance of the sensitive attribute is 0, that doesn't necessarily mean that the model is perfectly fair. If it's non-zero, it doesn't mean that the model is unfair. So I think there needs to be some more work figuring out how do we communicate what exactly that importance value is. Second is, how does this analysis change when we're evaluating explanation methods in general, like LIME or SHAP, versus a specific explanation for a given data point and a model? I feel like these are two slightly different or very different problems, and it's unclear, what strategies are useful in what situation. So finally, we wanted to show a really preliminary approach, more of a proof of concept of how we might generate explanations that are intrinsically fairness preserving. And so what we did here was we just added a constraint to the original LIME optimization problem to make sure that the group fairness of the learned decision boundary or the approximated decision boundary is the same as the black box, or as close to the black box as possible. And this graph shows that this was successful in minimizing the difference in, or the mismatch in, the demographic parity of the approximated versus the black box model. But again, this is just really first steps. And so just to wrap up, I just wanted to give a couple of higher level takeaways that we were thinking about as we were working through these examples. The first is that we need more nuanced ways of evaluating explanations beyond fidelity, because there are many other properties of a model, for example, fairness, that we also care about, and that depending on the application that we're using the explanation for, we would hope that the explanation also captures. And this leads into the second takeaway, which is we need to think about how to make clear what is and is not communicated about the model by a given explanation. And maybe it's impossible to capture every single property of the model in a single interpretable, understandable explanation. And if that's the case, then we need to think about how exactly we're going to make it clear that we're not attempting to explain every single aspect of the model. And yeah, we think this is really interesting preliminary work and hope that it sparks discussion and further work down the line. Thanks for your time.